I am one of the architects for GlusterFS, a distributed file system. In past lives, I've worked on several others. I haven't worked on distributed databases, but I stay in good touch with a lot of people who do, because we actually use a lot of the same bag of tricks. So, it's a pretty broad background on, the problems that can occur. And one of the things that comes out of that is the observation that it may be the developers who choose the data store that they use to go with their application, but they're not the ones who bear the brunt of the pain when things go wrong. When your data is missing, corrupted, your performance is bad, it's you guys who are going to have to deal with it. So it's very important, I think, to have that perspective while those decisions are being made and to have the background to make it. Hence, that's why I'm here. So we're going to cover two major dimensions of how your data may be stored. The first is the physical. What kind of physical infrastructure do you want to use to store your data? The second is the logical structure. Do you want a database? Do you want a file system? Do you want an object store? That kind of thing. I'm going to talk about a bunch of new technologies and how they affect these kinds of decisions. It's really hard to get your head around all of the things that you need to know in order to figure out what the right data store is for your needs. Certainly, you're still going to have some questions in your heads after we've gone over all this. So, we can certainly have subsequent discussions about that. And throughout, after each major section, I've tried to put some recommendations. Now, these are my recommendations based on my perspective. I absolutely do not intend them to be gospel, to be applicable to everyone else. So, just look at that as a snapshot of how you might think about how to make those decisions. So, as I said, we're going to talk about the physical and we're going to talk about the logical. On the physical level, you essentially have four basic choices. You have direct attached storage, which is anything that's private to one host. That includes things like server-side flash. Some of the newer technologies that we're going to talk about at the end are probably only deployable initially in this form, the various forms of FRAM, MRAM, et cetera. They're probably not going to come in a separate enclosure. They're going to be something that you slot into your servers. We're going to talk about SANs briefly. We're going to talk about NAS, and we're going to talk about more general distributed systems. The so-called shared nothing model. Systems where each node has private storage, but it's presented to servers and to the compute complex as a single logical entity. Now, at the logical level, we again have four possibilities primarily. These do shade into each other quite a bit. You'll find that a lot of projects actually cover more than one. For example, as I said, I work on GlusterFS. It's a distributed file system. But you can also do block storage. You can also do object storage through the same infrastructure. Mostly other distributed file systems, at least, tend to have this same property, that they're accessible through other APIs as well as looking like a file system. So you have, among your logical possibilities, you have a traditional relational database, rows and columns, et cetera, Oracle, MySQL, Postgres, et cetera. You have the entire NoSQL space. So that gives you an even broader set of semantics and behaviors. You have file systems and you have object stores. So as we go through these are the basic categories I'm going to be trying to divide things into. So the physical level. You've got local disks. Now, as I said earlier, it doesn't necessarily mean a disk. It can mean anything that's inside a single server. It's simple. It's cheap. And who here doesn't understand how to deploy disks within servers? And is there anybody really? didn't think so. The other thing that's nice about local disks is that there's no coherency problems. If you only have one server that's accessing that disk, you don't have problems with write hazards and consistency and so forth for those accesses. That's handled by the operating system for you. So that's pretty nice. On the other hand, you're limited to, in terms of capacity and performance, to what you can fit inside and configure within that one server. The biggest negative is that this approach does not address the issue of server failure. If you're running a large-scale system, you're going to have to deal with the issue of server failure. That's pretty much universal nowadays. So you're going to have to need to roll your own heartbeat failover. There's lots of tools out there to do that, but you're still going to have to set it up yourself separately from setting up the storage software itself. And of course, you're going to need to replicate that data. If you're using some of these newer high-performance types of storage, that's actually going to take away a lot of the performance you just gained. So it's something you need to think about and manage very carefully. Our next contestant is SAN. This is something that typically people are not choosing for new deployments for a variety of reasons. It's more often something you're going to inherit or have pushed upon you by your management. It does have advantages. I mean, despite the fact that I work on distributed file system myself, I am not a total enemy of SAN or NAS. They have their place. The people who work on them, who put them together, have done an excellent job on reliability. There's often very rich functionality in there. I would say we in the open source distributed file system world are often playing catch up there. They can have very good performance and capacity, and they can scale to huge capacity. That's great. That's wonderful, if you have the money to do it. Is there anybody here who operates on an infinite budget? I always ask, oh, cool, you work for NSA, huh? No. I always ask because that's where I want to send my resume to. Most of us are pretty budget constrained. Even though the stuff I work on is open source and it's a cost play, we still, among our users and our customers, get enormous pushback to reduce the cost still further. For example, by improving storage efficiency, by increasing the amount of data that we can pack on any one server. People want to buy fewer servers. They want to buy fewer disks. I've worked with some of the richest companies in the world, and they have more money to spend than anybody, and they're not spending any of that money on IT. They pretty much want to. They're putting as much pressure as anybody on us to reduce costs. So that's, I think, one of the reasons that SAN tends not to be a preferred option. Then again, maybe it's just my perspective, given what I do. The other disadvantage of SAN is the fact that, like direct attached storage, it doesn't address server failure. At least you don't have to replicate now. That's handled within the disk array. But you do still have to deal with the issue of server failure with your own heartbeat failover, et cetera. NAS. Now, NAS people are going to hate me for this, but it's basically the same as SAN as far as this model is concerned. I'm not saying they're not different. It's a different skill set, different set of concerns around performance, a different set of protocols. But when you come down to the pros or cons, back here, reliability and in-array functionality, directly analogous in the NAS world. Performance and capacity, if you're willing to spend the money, exactly the same in the NAS world. Still doesn't address server failure. Same in the NAS world. So while there are differences, for the purposes of these particular criteria that you would use to select a storage system, they're pretty much going to give you the same picture. Next, we get to the fully distributed systems. Now, this includes not just things that you have sort of known about for the last 20 years or more. It also includes things that are being called server SANs or hyper-converged storage. I love that hyper-converged. Because we never had compute and storage on the same servers 50 years ago. So, you know, one of the advantages, I'm real keen on the advantages, you know, highly scalable. It can be very inexpensive if you're using the open source alternatives. You don't have to, because it's not wrapped in tin, you can just get the software, download it. Usually it's, you know, for something like Ceph, Gluster, et cetera, it's usually in your distribution's repos already. So on the mixed side, now a modern design of a distributed file system or a distributed database or anything like that addresses server failure quite well. There was sort of a school of design for these things, which is mostly faded at this point, where there's a single metadata SPOF and bottleneck. You know, avoid those. And then there's a downside. I hate talking about this part because of what I do, but there really is. Distributed file systems and distributed databases can be difficult to deploy. It can be difficult to work around the performance anomalies. They do have performance anomalies. Once you go distributed, things that used to be fairly cheap and easy on a single system become pretty complicated and expensive, and it's not always where you would expect. You know, who knew that a rename is like a really, really, really awful thing to do? Who knew that file creates would be impacted much more than reads and writes? If you've dealt with these things before, you probably do know that. You probably know it all too well. If you haven't, it might be a bit of a surprise. So it can be really tricky to get your head around you know, the trade-offs that are involved there. So I'm going to go over a couple of those in particular. I'm trying not to make this specific to distributed file systems. Most of what I have to say here does apply to distributed databases and distributed object stores as well. But, you know, I'm still talking from what I know. The biggest issue in any of these distributed data stores is replication and consistency. Does anybody recognize this picture here? It's a bit of a visual pun there. It's a split brain. So if you want to deal with server failure, you have to be replicating your data between multiple servers. Once you're doing that, you have the possibility that the copies of that data that's on those multiple servers gets out of sync somehow. This can take different forms depending on the replication strategy that your data store is actually using. It can be more or less prevalent. It can be more or less trouble to resolve. But it's always going to be a problem. It's going to be a performance problem, and it's going to be an operational problem when your users come screaming to you that their directory full of research results, or whatever it is that you're storing there, doesn't seem to be there. Usually you'll look on the back end, you'll find, yes, it is there, but for some reason your distributed data store kind of lost track of where it was. So there's actually a series of posts by Kyle Kingsbury that I linked to here. He's done some absolutely amazing work, mostly in the database world rather than the... one of my nightmares that makes me wake up sweating is that I'm going to, you know, get up, go down to the couch, get out my computer, look on Twitter, and it'll say, hey, here's my results from running the Jepsen tool on GlusterFS. Oh boy, because I know we're in trouble. He always finds stuff. Everything that he has run these tests on, you know, he has a particular set of tests that are exercising consistency behaviors. He has found bugs. And when people find data loss bugs or data consistency bugs in your code, and then they write a blog post about it, and they tweet about it, and everybody's talking about it, it's going to be pretty darn embarrassing. And I have no illusions that somebody of his talent and skill will be unable to find any bugs in the code I work on. You should definitely go read that series. It sheds some very interesting light on just how difficult a problem area this is, how you can get yourself in trouble, how seemingly innocuous differences between one way and another way of doing things can actually lead to very different results and very unpleasant results. Another big issue, this is one that we get slammed on quite often, is rebalancing. The whole point, well, one of the whole points of a distributed data store is that you can add or remove capacity by adding and removing nodes. Well, as soon as you do that, according to most of the methods that you would use to have placed that data, you want to migrate some of that onto the new servers to redistribute the load. So in this picture, we had the blue, yellow, green data sets, and they were distributed across three servers. We added a fourth server, and our whole picture of how that data is replicated and distributed has to change, because obviously you don't want to replicate between two buckets that are on the same machine. Then that machine going down takes out two copies. Now, rebalancing across a large multi-petabyte data store containing potentially billions of files or objects or whatever is going to be a time-consuming process, no matter how you slice it. It's going to be a resource-intensive process. So on the one hand, you want to try and keep that time to bring things back into balance down from, say, weeks to days. On the other hand, you do not want to implement what amounts to a denial of service for your ongoing I/O stream. If your rebalance traffic is totally swamping the system and it can't service normal I/Os anymore, you're definitely going to get some complaints. So this is actually one of the things that you can use as one of those sort of probing questions when people are touting the benefits of their distributed data store. How well do you handle the rebalancing cases? What do you do to ensure that you don't starve regular I/O? Surprising number of systems do pretty much nothing. They will starve regular I/O. And then there's varying levels of sophistication above that. And of course, no talk about distributed systems would be complete without a discussion of CAP. How many people here know about the CAP conjecture or theorem, as it is variously called? So the basic idea here is that there are three properties that your distributed data system can have: consistency, availability, and partition tolerance. I'm not going to go into terrible detail. There's endless bickering about the finer points of what these definitions actually mean. The intuitive definitions are probably good enough for now. A lot of people say it's a pick two kind of thing. And I think that's actually terribly misleading. It's not pick two. You can have modalities, so you can switch from one mode to another where you're favoring different properties and different operational states. You can also have medium amounts of more than two of these. You can trade off absolute consistency to get a little bit more availability, et cetera. So that's why I like to show it as a cube here. If you start from the center point, that's the corner that's closest to us, you can go out along any of the three axes, but you can't go around the back. You can't go to that furthest point that's the absolute maximum of all three properties. If you're at one of these fairly well-defined points that represent the diagonally opposite corners, you can't keep going without sacrificing some of that property. If you're at A and P, so that's the far corner of the red face, you can't suddenly gain more consistency without sacrificing some of those properties you already have. I figured the cap cone and the cap tetrahedron were going to be even more confusing. Don't just think of it as the triangle. The triangle that's usually used to show this, I think, just leads you down a wrong path. So, recommendations on the physical side. Even though I love distributed storage, I say use local whenever you can, because sometimes you're not. Sometimes you're going to need that data be shared, either for resiliency reasons, or just because it's being actively used for more than one server at a time. Some of the newer technologies the FRAMs, MRAMs, PCMs, things like that are probably only going to be available in that form. Anything that's sitting on the PCI bus or the memory bus, certainly is in that category. When it comes to SAN or NAS, they're not dead. I'm not going to say never ever use them, but they're probably not going to be the most common or popular solutions for the reasons that I've given. And even though distributed storage is a wonderful, awesome, amazing thing, do be wary of its drawbacks and its trade-offs. Believe me, as a developer of a distributed file system, I hear all the time, practically every other day on Twitter, about how Gluster has ruined my life. That feels great. But it's not untrue. For these people who have trusted us and have deployed our system and then had it fail in a spectacularly hard to debug way, it really was traumatic for them, and you can't blame them for expressing that. Well, yeah, I do, but. So moving on from the physical to the logical side. For a lot of things, it's very old school, I guess, but relational databases are wonderful things. The relational model has a long and proud history. I love saying up in public, ACID is great. It's a very mathematically rigorous model. It's a very flexible model. All of these things that go with that, the ability to do ad hoc queries, the fact that you have this, many, many years of people thinking very hard about how to strategize ways to execute a query quickly, that's wonderful. Then you get to some of the downsides, and this is what led to the whole NoSQL movement. Having inflexible formats, the need to normalize your data. Now, as soon as you normalize, one of the things that you're doing is you're almost, by definition, creating a point of contention for that data that you have normalized. If the idea is that you only have one piece of data stored in one row and one column, then anybody who needs that is going to be contending with anybody else who needs it. The difficulty adding columns, and how many people here have tripped over the difficulty of adding a column to a MySQL database? It's gotten better, but still not people's favorite thing about relational databases. And actually, it's kind of funny that what a database is doing internally when you add a column is not that dissimilar to what we're doing in a distributed database or file system on rebalance. They now have a new set of rules for how they're supposed to lay out their data, and they need to take data that was set down according to an old set of rules and transition it to the new set of rules. So some of the same concerns actually apply there. Most relational databases have good replication or scaling stories. It's a matter of degree. Typically, those replication and scaling stories don't go quite up to the hundreds or thousands of nodes that you would see with some of the NoSQL options. But it's certainly not the case that you're stuck on one server with old school failover. I mean, they've moved a long way beyond that. Our next option in the logical space is, I kind of hate the term NoSQL because it means so many things. Can anybody here recognize all of these logos, by the way? I actually didn't recognize the sort of starbursty one down on the graph one. That one I actually didn't know until I was doing these slides. The problem with NoSQL is that even though there's some common principles, there's also just so many axes of differentiation between them. And a key value data store like Voldemort at the top left, in terms of its data model, it's just completely different than say Cassandra or Riak, which are below it. you know, in terms of consistency behaviors, they're all over the map. In terms of performance profiles, they're all over the map. Some are write optimized, some are read optimized. Some are small object optimized, some are better with larger objects. Some of them have more or less support for things like secondary indices. You know, there's so many differences between them. But so when we talk about NoSQL, we're essentially defining a space, a big space with a hole in it. That hole is SQL, and everything else is NoSQL. So you know, you have all these different data models. You have all these consistency models. And I just cannot stress enough how important it is for the people who choose and the people who are going to deploy any kind of database to understand the consistency model. This is where people get in trouble. All the stories you see about, oh, well, we chose NoSQL database X and it sucked, so now we use NoSQL database Y and it's awesome. Most of them actually come down to consistency, that the old one didn't have the consistency behavior that they wanted. Very generally, because you know, the people who work on these things do all, you know, talk to each other and trade ideas. We're all working out of the same algorithmic playbook. Generally, there's very good scalability. There aren't these metadata spoffs that you get in some other systems. A lot of the most cutting-edge work in solving some of the fundamental problems of distributed data, stuff that's actually applicable to file systems, stuff that I keep a close eye on, is being done in the database world by the NoSQL people. So for example, you know, even though I'm a file system guy, VLDB is going to be one of the most interesting conferences for me to follow, because that's where a lot of these guys are presenting their ideas, their observations, their solutions. One of my roles within my project is actually to try and bring that into the file system space, where most of my colleagues, sadly, are not paying much attention to it. Again, because there's so much in common between distributed databases and distributed file systems, you find some of the same dark alleys as far as consistency, as far as performance. Because these systems are not constrained by a single 30-year-old API, the POSIX file system API, they've branched out in new directions. So they add even more confusion, if you will, more advanced technology, if you prefer that, in terms of things like vector clocks, CRDTs, which are data structures that converge and lower your coordination requirements. So sometimes these are just things that they're unfamiliar. They're not bad. They're not problems. They're just things that people don't understand them and don't understand the implications of using them, or don't understand the cases where they should be using them. And they try and use this new thing as though it's an old relational database, and they get themselves in trouble. So file systems, fortunately, this is one where we're probably pretty familiar with what the semantics are. As I said, got a lot in common with the database community. The distributed database community. We actually have less so with the relational folks. No particularly good reason for it. It's just how the communities interact. The big advantage, I think, of a file system is that it's very familiar. Everybody knows how to read and write files. Every library, every tool knows how to read and write files. They know how to navigate that namespace. They know how to do open, close, read, write, et cetera. Okay, so people might be a little bit fuzzy on, say, extended attributes. You know, some of the weirder kind of off-to-the-side functionalities. There's a lot of misunderstanding about some of the details of what's expected to be atomic and what's not, when durability is guaranteed versus when it's not. But mostly people understand what a file system is and what it looks like and how to work with it. And that's huge. I mean, if you have an existing application that's already using local files or already using NFS or anything like that, you know, you might not even be able to change it to use a completely different data model instead of semantics. You want another file system. You just need one that's more scalable. So this is actually, by far the biggest advantage of a distributed file system. Now, the disadvantage is that some of these features and requirements are very, very hard to implement correctly and with good performance. Cross-directory rename. It's like every file system implementer's least favorite feature, especially in the distributed world, because now you have the possibility that you're renaming not only from one name to another, but essentially from one server to another. And you have to make sure that you don't create two files at the same path that are actually completely different things. Byte level reads, and especially byte level writes that might overlap in arbitrary ways. None of the other data models have exactly this problem. Block storage, you don't have overlaps at all. Databases of various sorts, you usually have a column boundary. So the number of possible overlaps you have is relatively small. With file systems, you're constantly having to detect overlapping writes, make sure they're ordered correctly, make sure they're persisted correctly. And that has a cost. But I want to emphasize that this is only applicable to some features. Any self-respecting distributed file system implementer knows to optimize the easy cases. If you're generating nice block-aligned writes that never overlap with one another, you're going to be using a much simpler path. We're going to recognize that. I mean, we're not total idiots. Which brings us to object stores. The basic idea behind an object store, something like Amazon's S3, OpenStack Swift, et cetera, was to take something that was kind of roughly flavored like a file system and simplify it. So there's usually only a 1 or 2 level hierarchy, not endless subdirectories. You're getting and putting whole objects. You're not doing overlapping reads and writes in the middle. Most of them, at least to start with, didn't support rename at all. If you want to put something in a different place, you put it again. Now, supposedly this makes them much more scalable than distributed file systems, and I'm basically going to call BS on that. Most of the hard problems are still there. Either the person implementing the distributed object store still has to deal with them, detecting and handling faults, replicating, repairing, rebalancing. These are all still very much there for an object store. Other problems have just been pushed to the user. So you end up with sort of a variation of Greenspun's 10th rule, which I'm probably going to misquote slightly. It was that every sufficiently large program contains an ad hoc, informally specified, bug-ridden, slow implementation of Lisp. Well, in this world, it's kind of the same thing. It's an ad hoc, informally specified, bug-ridden, slow implementation of a file system. I hesitate to think about how many times I've seen people decide, oh, we're just going to do this with an object store instead of a file system. You guys have too much overhead because you're a file system. And then what do in the application? They reinvent half of file system functionality that was missing. And through no fault of their own, because they're not experts in this field, in distributed systems and in file systems and so forth, sometimes, just once in a while, they have bugs in that implementation. My take on it is that if you use the subset of file system functionality that overlaps with object stores, you'll get almost the same simplification, and you don't have the sacrifices. In particular, you're not giving up the consistency and durability guarantees, which a lot of applications, whether they do so explicitly or implicitly, do rely on. A lot of people don't even know exactly what their durability requirements are until they've written something and tried to read it back and it wasn't there because the update hadn't propagated through the system yet. And then they say, oh, well, I expected that to be immediately durable and consistent everywhere. You didn't say so, but the requirement was implicit there in how the rest of their system worked on top of that. So, recommendations. I'm actually, despite being a file system guy, a big fan of databases. They were built, they were designed, they were thought of to facilitate searching and querying. That's something that they will always do better than file systems or object stores. It's in their nature. You do have to navigate a very complex field. I could give a whole different talk about all the different types of databases. But you really need to think very hard, and both developers and operators have to think very hard about what the consistency needs are, what the performance profile is that they're looking for, et cetera. And always remember, if you make the wrong choice here, it's really hard to recover. You're going to be doing format conversions. You're going to be migrating gigantic amounts of data. This is one thing. It's not like changing a line of code. It's not. We've had a couple of talks just now about deployment of new code and packaging. It's not like that. This is going to be a long, painful process if you have to change your mind about this. I think file systems have their strength with the compatibility and familiarity. Everybody knows them, can work with them. And they work really amazingly well for hot or warm data, not cold data so much, although my management's going to kill me for saying that, that is accessed via a known path. Block storage on top of a distributed file system actually works amazingly well. It's actually a really easy access pattern for us as a file system to deal with. So the overhead is actually not all that much. Object stores on top of file systems work reasonably well. When you get into the really vast seas of data, the stuff that Facebook's doing with Haystack, for example, okay, then an object store might start to make more sense. But you're going to lose that ability to sort of dual access this data as files as well. Let's talk a little bit about some new technologies. I had to include one software technology because most of what I'm going to talk about is actually hardware, and that is erasure coding. It's a generalization of the RAID concept, except that instead of having just one parity, you can have 2, 3, 5. It's really pretty flexible. Basically, any k out of n above certain minimums can work. It's not that common in storage systems now. There are a few out there that do it. I'm proud to say Gluster has recently become one of them. I know Ceph has some functionality in this area. HDFS is working on it. Swift is working on it. None of them are terribly mature, but everybody's working towards this because it offers great storage efficiency. Instead of doing straight replication, where you have 2x or 3x your usable data, you're talking about 1.2, 1.4, 1.6, pretty much always less than 2, and you're getting double failure protection, triple failure protection. It's really pretty valuable. Downside, terrible performance. All of this fetching, doing math, storing, et cetera, particularly during rebuilds, has a cost. So that's not what you want to use for your hot data. You want to do tiering, or you want to use it for colder data. And then we start getting into all of the faster, newer technologies. Flash is no longer going to be the speed king. Everybody's thinking, oh, we got SSDs, they're so fast. Not next year. So these numbers are actually taken from a paper that was at FAST earlier this year. So you can see with Flash, you've got 108 microsecond read latency, 37 microsecond write. Flip that on its head and you've got what PCM does. That has some pretty serious implications for where you would use each one. You don't need me to tell you what those implications are. I think that's going to be pretty obvious. The density is not quite as good as flash yet. All of these new technologies are improving rapidly. There's power consumption issues with all of these, including disks, including SSDs. Phase change, one of the big bugaboos that's prevented it from being more common is temperature sensitivity. Then we've got FRAM or FERAM, even faster. The equivalent problem here is fatigue or imprint, that the bits kind of lose their ability to change. MRAM, we're getting into memory speeds here. Again, not as dense, not as cheap, but it's coming. We got Racetrack, Sonos. And there are people thinking about how to do this. What do you do when you have something with memory-like performance, but it's durable? This is going to change a lot. This is going to change our entire way of thinking about storage versus memory and how they relate to one another. At the other end of the scale, spinning disks, we have larger capacities. We have heat-assisted recording, patent media, shingled disks where the tracks overlap. So if you overwrite one, you have to overwrite the entire band of several tracks. This is going to be really terrible for small updates, but your capacity goes way up, and it doesn't affect your performance for strictly sequential writes. So this is why I think that log-structured file systems, which have kind of been a little bit of a backwater for a while, are going to come back to take advantage of shingled disks. So you have these really fast kinds of storage at one end. Now you've got a really slow kind of storage at the other end. So you're going to have a lot of layering. You're going to have, let's say it's MRAM, and you're going to have flash, and you're going to have normal disks, and you're going to have SMR disks, all within one system. You're not just going to be thinking about how to tier across these based on performance. It might be power, durability. And the bottom point is really the most important one. If you try and manage all this in your head or manually, it's going to drive you nuts. You're going to need tools. You're going to need a lot of this to be automated. So don't be afraid to choose multiple storage types, multiple physical storage types, multiple logical storage types for different pieces of your application. They all have strengths. They all have weaknesses. The key is that you need to have a plan to make them work together. And you don't want just to have islands that are separate because they're separate. You want to have something where you have this storage because it's really good for reads, and this storage because it's really good for storage efficiency. Things like that. And you're definitely going to want to have a plan, and you're going to want to have tools, whether they're self-developed or something that already exists, because you're going to have more layers than you've ever seen before. You're going to have data moving up and down 6 layers of your storage hierarchy. And that's going to be really difficult to manage. And in the next 3 minutes, does anybody have any questions? Please come up to the mic. Nope. Got my hopes up. Well, thank you all. And if you do come up with questions later, I'm easy to find.